learn about regression.
I'd like to thank the organizers very much for inviting me. This is joint work with Jocelyn Chi. Jocelyn, stand up. Jocelyn will answer all the difficult questions. So, well, we are concerned about least squares regression, and we are using the statistics notation. So Petros already did a little intro, but we are starting here from the Gaussian linear model, where we have a design matrix X. That is a tall and skinny matrix with linearly independent columns. It has full column rank. And then we want a parameter beta 0, which is in general unknown. But what we do have are observations y, which are corrupted by error. So the observations, the observation error is y, and the error is epsilon, and it's normally distributed with variance sigma squared. So what one does computationally, one solves the least squares problem. So one picks a y, one solves that least squares problem. If the matrix X has full column rank, then one can get a unique maximum likelihood estimator beta hat, which can be expressed in terms of the matrix X. So we have an inverse here that's possible because X has full column rank. So the thing is now, as Petros already mentioned, these matrices are huge. They can have many rows. So what one can do is one can do a row compression. So it's the same matrix S that Petros used, and use only a few of the rows. So one reduces the rows, one reduces the observation, and then one tries to get a minimal known solution beta tilde. So our objective here is to determine the combined mean and variance of the two types of uncertainties we have. Uncertainties due to the linear model and uncertainties due to the randomization. So our inspiration was the groundbreaking work by Ma, Mahoney, and Yu on a statistical perspective on algorithmic leveraging. So what I'd like to do is very briefly summarize existing work, and because it's Monday morning, I will do a lot of examples, and then give some structural perturbation about meaning deterministic ones. Then we condition on the model-induced, we review the model-induced uncertainty, and then everything together, and then a summary. Okay. Maybe I'll do this here. Okay, so there's a lot of existing work. I'm just looking here at row compression algorithms. There's also a way to work on the columns, for example, blend and pick by Heim and Sivan. And I'm not going to include it here. It's not any of the work on regularization that, say, Alex and Michael did. So there's a ton of work here on the randomized algorithms, as well as the statistical properties. So let's just start with some examples, some very simple examples. Here we have a design matrix. It has two columns. They're linearly independent columns, you can see, because here the ones correspond to zeros here. It has a left inverse. The left inverse has 1/2 here, because in that first column we have 2 1s. So this is a left inverse. That means if I multiply x from the left with this with that Penrose inverse, I get the identity. So I'm not giving here an observation y, but the maximum likelihood estimator then uses this pseudo inverse. And then we can look at, we attribute the uncertainty now in the model, we attribute it to y. So then the expected value of the solution from the point of view of y, because y is x beta 0, we take the expected value, and epsilon is expected value 0, and this here is the identity. So it's a very short review for the fact that the solution from the least squares problem is an unbiased estimator. We can also get the variance because we have 0 mean, so the variance is sort of quadratic, and we get this. Okay, we have that. Okay, now you do sketching. Let's fix a sketching matrix S to start with. Let's just look at it as a multiplicative perturbation. Here's a sketching matrix that has full rank. It has rank 2. It has a 1 here, meaning it samples the first column, and it has a first row, and it has a 1 here, meaning it samples the second row. So our sketched matrix is the identity, which is great because that means it's its own inverse. So when we put it into the, we condition then on the matrix S, it's fixed, and then we determine the expectation with respect to the linear model. So we get this, while both of these guys, their identities all over the place. So because the sketching matrix has full column rank, we get an unbiased estimator. And we can also figure out the variance. Again, this is the formula for the variance. Everybody inside is the identity, so that's what we get. So if you now look at the variance of this solution from the perturbed problem, you see it has increased with regard to the Löwner partial order. So in this case, the variance has increased. Now if we take another sketching matrix, again, the sketching matrix S has full row rank. The two rows are linearly independent. But the rows it samples from X are this one and this one. So now the sketched matrix is rank deficient. There is no inverse anymore, so we have to take the pseudo-inverse to get a minimal norm solution. So now this times this is not the identity anymore. It's just this. So in general, for general B0, this is not equal to B0 anymore, beta 0. So we have a biased estimator. And also, if you put this matrix into the formula for the variance, you'll see that the variance is singular. So to sum up, what we see from our little example is that if you fix the sketching matrix and if it preserves rank, then you have a left inverse. So you're allowed to take this inverse, and then the conditional estimator is an unbiased estimator. It has the same, it's equal to the same value that you would get from the Gaussian linear model. So you haven't messed anything up with the sketching in terms of bias. If the sketching matrix loses rank, you cannot take that inverse anymore. Then you get a biased estimator and the variance is singular. Okay, so in general, one doesn't have a fixed sampling matrix. So here we are doing uniform sampling with replacement. We are sampling 2 rows out of 4. So Sij denotes the various instances of the sampling matrix we can get. So the first row of S can sample any of the 4 rows of X. The second row of S can sample any of the 4 rows of X. So we have 4 times 4, 16 probability. So S11 says that, oh, S, because it's with replacement, samples the first row of X twice. S42 samples the 4th row of X, and then the second row of X. So you get these. So if we want to get if we take the expectation over S, we see it's an unbiased estimator. We have a 1/16 here because we have 16 different instances of S. Each of them can occur with the same probability. So in terms of, this is the deviation of the columns of S from orthonormality. In expectation, they are orthonormal and they're equal to the identity. Okay, so if we now use what we had from before to get the total mean, we condition sequentially. So we condition with regard to the linear model. After that, we condition with regard to the sampling matrix. So we get this here. And now we just have to sit down and work it all out. The expected value goes over all possible values of S, which in this case we can figure out. You sit down with paper and pencil, you have a lot of patience, and you get that. Well, that thing is not the identity. And that thing multiplies beta 0. So that means in expectation, you don't have an unbiased estimator. And in particular, 12 out of the 16 sketched matrices are rank deficient. Okay, so that's the little example. So as Petro said, the first thing in analyzing randomized algorithms is often to have structural deterministic perturbation bounds. So here we have our exact problem. We have to go with that a hat matrix, an orthogonal projector onto the column space of X. And because X in our case is a full rank matrix, the pseudo-inverse can be expressed in terms of X. So the range of the projector is exactly the range of the design matrix. And our solution, well, we have an inverse here, a pseudo-inverse, and it can also, I'm doing this because we need this, it can be represented as the pseudo-inverse applied to the projection of the observation onto the column space of A. Okay. Now there's the perturbed problem. Well, for the perturbed problem, the matrix is Sx, but we can't take an inverse. We can't construct the pseudo-inverse from that inverse because in general that matrix is rank deficient, plus Sx has many fewer rows than X. So we have 2 types of least squares problems to deal with. One with many rows, one with a few rows. We somehow have to compare them. So for that purpose, we construct a comparison hat matrix, which is with regard to the original matrix X. So this projector here has the same number of rows as the hat matrix. and its range is contained within the range of X, and it's exactly equal to the range of the original matrix X if that projector has full column rank, meaning our sketched matrix has full column rank. And then we can represent our solution as, again, this inverse, and then we have the comparison hat matrix here instead of the original matrix. So this projector is a little bit more general than what Michael and Garbash-Raskuti had. Our projector is equal to theirs when the matrix Sx has full column rank. But for rank deficient matrices, theirs sort of doesn't work. So here we are. Here we have the design matrix. So you see you have 2 columns and you have non-zero elements in 3 rows. You can see that in the projector here too. This is the first column, this is the second column, this is the first column again. So if we take a sketching matrix that preserves rank, like this one here, that picks the first 2 rows of X, the projector P, the comparison hat matrix, reproduces the first 2 columns of X because it starts out with X here and then this stuff here is full rank. However, if you have a sketching matrix that loses rank and that picks rows 1 and 4 of X, where we have a 0 here, you can see that only the first column of X is preserved, and because this thing is rank deficient, the other stuff is lost. So you can see that this projector gets only part of the range of the design matrix. It misses out on this column. So here we are again. So we can, this is our original solution. This is the solution from the sketched problem, and you can see we can write the sketched solution as the original solution plus the difference between the two. And the difference between the two is a difference between an oblique projector and an orthogonal projector. So the difference between the two solutions is proportional to the difference between the hat and the comparison hat matrix. So it's a very nice geometric way of looking at things. So from that we can get multiplicative perturbation bound, which may only be of interest to the numerical people in here, but this is only one slide, and then we go back to other things. So here we have the condition number of the design matrix in the 2 norm. That is the ratio of the largest over the smallest singular value. It tells you something about how the matrix deforms a unit sphere. If that condition number is large, then when the matrix acts on the unit sphere, it produces an ellipse that has a very huge aspect ratio. And then we're also interested in the angle between the range of the design matrix and the observation vector y to see how much can the matrix capture the observations. And from the previous expression, we can get a bound for the error in the sketched solution. We can view this, the difference between the 2 projectors, as the perturbation. That is amplified by the condition number of X, the aspect ratio, over the cosine of the angle. So that means there's a lot of amplification if the condition number of the matrix X is high, and if Y is very far away, the observation is very far away from the design matrix. So the design matrix has a really hard time capturing the observations. And that's also when a least squares problem is ill-conditioned in the deterministic setting. Okay, so these bounds are tighter than what has happened before. Okay, so now let's look at the model-induced uncertainty. Let's assume S is fixed. We fix a sketching matrix or a sampling matrix. So here we have the solution. We can, from the solution, we can see that we can get the conditional mean. S is fixed. So the only thing that has a non-zero expected value is y, and expected value is x beta 0. So if the sketched matrix preserves rank, then the pseudo-inverse is the left inverse. We have the identity here, and the solution is an unbiased estimator. However, if the sketched matrix loses rank, then you can see by adding and subtracting beta 0 here that we have a rank deficiency, a deviation from unbiasedness. So we can see that this is what we want, but this is what we get. So that means our deviation or our bias increases with the rank deficiency of this thing, of the sketched matrix. Okay, so for the variance we can, the variances are always more unpleasant because they are quadratic, right? So we have our hat matrix for the original problem, the projector onto the range of X. Then we have the comparison hat matrix. This is the original variance, which we can also write like this for comparison, so that we can express the variance of the sketched solution as the variance of the original solution plus a mess. But if you look inside this mess, what you have here is PP transpose minus P sub x. So this is the hat matrix, the orthogonal projector onto the range of x. That matrix is nice. It's symmetric and it's idempotent. It's being compared to PP transpose. Well, if P was also symmetric and idempotent, this would be 0. So this thing here is the deviation of the comparison matrix from being an orthogonal projector, from doing the right thing, from capturing the column space of X. Okay, so here's the summary now. So we fixed the sketching matrix, and we wanted to see what does that do to the biasedness of the solution. Is it still an unbiased estimator or is it not? So we saw that if the sketched matrix still has full column rank, the sketched solution is unbiased. If it doesn't, then the bias increases with the amount of rank being lost by the sketched matrix. The conditional variance is close to the model variance if that comparison hat matrix is close to doing its job and reproducing the column space of X. And if X is also well conditioned with respect to left inversion. And if the sketched matrix loses rank, you have a singular variance. Okay, so now if we put everything together, that's great, I'll finish early maybe. Okay, so here we are. Now we put everything together. So what we can show is that the total mean, if we look at the uncertainty from the randomization and the uncertainty from the linear problem. So this is our, what we would like, and here is what we have. So it's the expected value over all instances of S, and then we look at how close that is to being the identity matrix. And we are doing that over all instances of S. So we can see that that's the expected deviation of the sketched matrix from the identity. So you average over all sketching matrices S. Try out how close this thing is to being a left inverse. You can do that by subtracting the identity. So that means the total bias is proportional to the expected deviation of the sketching matrix from identity. And the variance is a mess again, but you can see here we have two terms. So the variance of the sketched solution is equal to the original variance, and then there are two other terms. This is the expected value of the comparison hat matrix from being an orthogonal projector onto the column space of X. Before we had just this expression, now we are averaging over all sketching matrices, and then here in the variance we have the deviation of the sketched matrix from full column rank. So these are the two things. So these are equalities, right? So this is what the variance is like. It's not pretty, but that's what it is, and we can get the geometric picture out of it. Okay, so now I wanted to look at two cases. Again, so we were going to look at a best and a worst case. So if we look at a design matrix X, what's the best design matrix we can sample from? Well, as Petrus already mentioned, they are leverage scores. So it would be a matrix whose columns are columns of a Hadamard matrix, because you see X, it's an orthogonal matrix. It has orthogonal columns, not orthonormal columns, but the mass is well distributed. There's no 0. Everybody has magnitude 1. And the two columns are linearly independent. So the mass is as uniform as it gets. This is the orthogonal projector onto the range. And so now if we sample two rows uniformly and with replacement, then the expected value, if we look at the deviation of the sampled matrices from rank deficiency, there are 16 instances of the sampling matrix, which I showed at the beginning. We see that this is the identity. It's sort of 1/4 of the identity. And if we look at the expected deviation of this matrix of the P from being an orthogonal projector, we get this. Okay, so you can also do that with the worst case. A matrix that has highly concentrated mass and has bad coherence. So this is as bad as it gets for a matrix with two columns, right? The mass is, so it's a matrix that has two linearly independent columns, and the mass is concentrated upstairs. So this is the orthogonal projector that goes with it. And now if we look at if we average over all sampling matrices and look at the expected deviation of the sampled matrix from full column rank, we see it's minus 9/16. So it's more than twice as much as in the best case. And similarly for the orthogonal projector. So one can compute these things. The question is now, how does one make sense of those? But these are not bounds. Those are equalities. So the problem here is now how does one interpret these things? So to summarize, I've looked at randomized row sketching for full column rank regression, and we did not look inside the sampling matrices except for the examples. So you can take any sampling matrix and apply that framework. So we got exact expressions for the uncertainties, combined uncertainties due to model and randomization. And we introduced the comparison hat matrix to allow comparisons between the sketch problem, which has many fewer columns, and the original problem. We got deterministic bounds, which are tighter than existing ones. And we saw that the total mean and variance are governed by the expected deviation of the sketched matrices from full column rank and the comparison hat matrix from doing the job of the hat matrix, being an orthogonal projector. And we gave examples to illustrate the applicability. And then there's a paper on arXiv. And before I finish, I'd like to make a plug for two things. For one thing, we have a postdoc position in data science at NC State, so please apply. It starts next academic year, and then we also have a book series on data science, and we have 3 associate editors here, Michael and David Woodruff. So anything that is too long to be a journal paper qualifies to be a candidate for the book series. So we are awaiting your requests and interest in the book series. Thank you very much.
Thank you. And thank you for finishing early as well. We actually have time for questions, and I'm happy to take questions for my talk as well. I didn't want to do it before, just not to run long.
So if you looked at it, so if you sample the column under one of these normal wave rows based on norm sampling or leverage scores with large enough of them, then he's say something basically with high probability that it's an unbiased estimator and that the variance is then not non-singular.
So that would be the next step. We haven't looked inside the sampling matrices. So we were, we were inspired by the work that Michael and Binyu and Ping Ma have done. So we first sort of revisited their work, which was in a very global context. And so we haven't committed to particular sampling matrices. That would be the next step to do. Yes?
And so if this happens that becomes unbiased, do the issues with, is then the variance case kind of simple, or is it still like you can tune stuff to kind of optimize it? I mean, once it becomes
well, so I talked to him, did I talk to David Wooden or somebody? You could, of course, take the sketched matrix. If it's ranked efficient, you could regularize it.
Okay.
And then, but then it's not clear at all. No, Miles, right? Where's Miles? Then Miles has looked at those things. It's harder to analyze regularizing the sketched matrix, right? Isn't that what you said? You're the statistician, right? So.
Maybe.
Yeah, it's not at all. Okay, so this is all value free. We are not advocating anything. We're just giving you that framework and take it or leave it. So looking inside the sampling matrix, committing to particular types of sampling matrices, that's the next step. So yes.
Other question? Yeah.
Does it seem hard, like you were always able to just condition, fix the sketch matrix, so you fix that, then you analyze the randomness from the input. But I imagine often you also have randomness on the actual input matrix, which will change its leverage scores and change its...
Yeah, so, for me as a numerical analyst, that'd be round-off errors. And we have, there's a whole other can of worms. So this is all in exact arithmetic. So for me, the next thing would be to look at, well, what if the design matrix is afflicted with round-off errors? What do they do to everything? Yeah, so that's another thing to look at. So Jocelyn has plenty of work to do.
Any other questions? Okay, so let's thank the speaker again.